Happy Pi Day, everyone. We are now continuing on with crafting interpreters and going to take a look at for loops. So let's get started. For loops. We're down to the last control flow construct, the old C-style for loop. I probably don't need to remind you, but it looks like this. For var I equals 0, I less than 10, I is equal to I plus 1, print I. In Grammarese, that's adding a for statement to the statement list, and then this is a definition of a for statement. Let's take a look at the side note here. Most modern languages have a higher level looping statement for iterating over arbitrary user-defined sequences. C# has for each, Java has enhanced for, even C++ has range-based for statements now. Those offer cleaner syntax than C's for statement by implicitly calling into an iteration protocol that the object being looped over supports. I love those. For locks, though, we're limited by building up the interpreter a chapter at a time. We don't have objects and methods yet, so we have no way of defining an iteration protocol that the for loop could use. So we'll stick with the old vintage C for loop. Think of it as vintage, the fixie of control flow statements. Inside the parentheses, you have three clauses separated by semicolons. The first clause is the initializer. It is executed exactly once before anything else. It's usually an expression, but for convenience, we also allow a variable declaration. So this is either a variable declaration or an expression statement. In that case, the variable is scoped to the rest of the for loop, the other two clauses, and the body. Next is the condition. As in a while loop, this expression controls when to exit the loop. It's evaluated once at the beginning of each iteration, including the first. If the result is truthy, it executes the loop body, otherwise it bails. The last clause is the increment. It's an arbitrary expression that does some work at the end of each loop iteration. The result of the expression is discarded, so it must have a side effect to be useful. In practice, it usually increments a variable. Any of these clauses can be omitted. Following the closing parentheses is a statement for the body, which is typically a block. Desugaring. That's a lot of machinery, but note that none of it does anything you couldn't do with the statements we already have. If for loops didn't support initializer clauses, you could just put the initializer expression before the for statement. Without an increment clause, you could simply put the increment expression at the end of the body yourself. In other words, locks doesn't need for loops. They just make some common code patterns more pleasant to write. These kinds of features are called syntactic sugar. For example, the previous for loop could be rewritten like so. Var I equals 0, while I is less than 10, print I equals I plus 1. This delightful turn of a phrase was coined by Peter J. Landon in 1964 to describe how some of the nice expression forms supported by languages like Algol were a sweetener sprinkled over the more fundamental, but presumably less palatable, lambda calculus underneath. The script has the exact same semantics as the previous one, though it's not as easy on the eyes. Syntactic sugar features like Lox's for loop make a language more pleasant and productive to work in. But especially in sophisticated language implementations, every language feature that requires backend support and optimization is expensive. We can have our cake and eat it too by desugaring. That funny word describes a process where the front end takes code using syntax sugar and translates to a more primitive form that the back end already knows how to execute. Oh, how I wish the accepted term for this was caramelization. Why introduce a metaphor if you aren't going to stick with it? We're going to desugar for loops to the while loops and other statements the interpreter already handles. In our simple interpreter, desugaring really doesn't save us much work, but it does give me an excuse to introduce you to the technique. So unlike in the previous statements, we won't add a new syntax tree node. Instead, we go straight to parsing. First, we add an import we'll need soon. Oh, interesting. So this is actually not going to introduce anything into the AST. Interesting. Okay. I'm already kind of jumping forward to thinking about how we're going to implement this. And we can still do desugaring, but it's probably easier if we allow the for loop to be in the AST to some degree. All right, let's take a look. Like every statement, we start by parsing a for loop by matching its keyword. Here's where it gets interesting. The desugaring is going to happen here, so we'll build this method a piece at a time, starting with the opening parentheses before the clauses. The first clause following that is the initializer. If the token following the open parentheses is a semicolon, then the initializer has been omitted. Otherwise, we check for a var keyword to see if it's a variable declaration. If neither of those matches, it must be an expression. We parse that and wrap it in an expression statement, so the initializer is always the type of statement. In a previous chapter, I said we can split expression and statement syntax trees into two separate class hierarchies because there's no single place in the grammar that allows both an expression and a statement. That wasn't entirely true, I guess. Next up is the condition. Again, we look for a semicolon to see if the clause has been omitted. The last clause is the increment. Hello, Roger J. Mexico. Thanks for tuning in. So now we take a look at the increment. It's similar to the condition clause, except for this one is terminated by the closing parentheses. All that remains is the body. Is it just me or does it sound morbid? All that remains was the body. Huh. We've parsed all of the various pieces of the for loop, and the resulting AST nodes are sitting in a handful of Java local variables. This is where this desugaring comes in. We take those and use them to synthesize syntax tree nodes that express the semantics of the for loop, like the hand desugared example I showed you earlier. The code is a little simpler if we work backwards, so we start with the increment clause. If increment is not equal to null, body is equal to new statement block, arrays.asList body, new statement.expression increment. The increment, if there is one, executes after the body in each iteration of the loop. We do that by replacing the body with a little block that contains the original body, followed by an expression statement that evaluates the increment. If condition is equal to null, condition is equal to new expression.literal, true, body equals new statement.while, condition and body. Next, we take the condition and body and build a loop using a primitive while loop. If the condition is omitted, we jam in true to make an infinite loop. If initializer is not equal to null, body is equal to new statement block, arrays.asList, initializer and body. Finally, if there is an initializer, it runs once before the entire loop. We do that by, again, replacing the whole statement with a block that runs the initializer and then executes the loop. That's it. Our interpreter now supports C-style for loops, and we didn't have to touch the interpreter class at all. Since we desugared to nodes the interpreter already knows how to visit, there is no more work to do. Finally, LOX is powerful enough to entertain us, at least for a few minutes. Here's a tiny program to print the first 21 elements in the Fibonacci sequence. Cool. So our goal will be, by the end of this exercise, to be able to run this code, example LOX code here. So let me just pin this window real quick. All right, let's go back over to our OCaml implementation. Open up test.lox. Oops. And paste that in there. Okay, so hopefully we'll be able to get that running by the end of this. Now, here's where I may be deviating from the book a little bit. I like the idea of doing desugaring here, but the desugaring is all implemented in the parser. And I am not writing my own parser. I'm using men here in OCaml to do the parsing for me. So as much as I like the idea of desugaring here, and I would love to be able to implement this, I don't think I really can. So I may have to kind of deviate a little bit. Let's take a look. Copilot's probably going to give me a for thing right here. Declaration, expression, semicolon. That's pretty bang on right there. So left parentheses, declaration or an expression, a semicolon, another expression, a right parentheses, the statement, and then it's constructing this for thing. Now, it could be that instead of constructing this for statement, I could, in here, construct some other AST node. Right? So that could be the case. Okay, so we have I declaration, C expression, U, B. I don't really know why they assign those variables, but yeah, let's change those out. I want this to be D for declaration. I want this to be A for assignment. I want this one to be C for condition, and I want that one to be What do we want to call that? We want to call that like the body. Yeah, we'll call that B. All right, so we changed everything there. D, A, C, and B. So the simple thing for me to do right here would actually be just add a for statement to the AST and handle this in the interpreter. So maybe we'll do that first, and then we'll come back to see if it can implement it using desugaring. Let's go to AST. Let's go to our statement, add a for statement, and then add it to print AST. I don't really care how it implements it, so we'll just let Copilot do its thing. It's going to complain because it's because of the compilation stuff. And then eval will start implementing it in there. Okay, for statement. For statement is made up of, I think we call it D, declaration assignment, condition, block. Okay, so this is basically the desugaring, but happening more on the eval side. So it's basically doing the while stuff, right? Eval statement, scope D. Interesting. We're also not really handling the fact that you could leave out one of these conditions. That's true. Let's take a look at our test logs. That's using a var. So let's ignore A for now. And we're going to, while eval expression scope C is equal to literal boolean true, do eval scope B. That looks correct. Okay. Let's go to Dune and run this thing. Sure, why not? We'll wait. We'll do that some other time. Okay. All right, let's do Dune exec OCaml logs test.logs. Okay. This expression is type statement, but an expression was expected to type expression. Eval scope C. Eval expression. Condition is a statement. Is that what it should be? Let's open up the AST again. This would be the var statement, then an expression. This one also should be an expression. And then that one is a statement. Okay. Okay, let's try recompiling, see what it thinks now. Okay, now we need to go back to our print AST and fix that. And print statement init, print string, print expression, condition, print string, print statement. Let's make this print expression. Okay, so now we have this expression as type declaration option, but an expression is expected of type statement. Okay. So now, because we've done this question mark here, it's saying that it's actually going to wrap that in an option, right? Let's do a simple case for now. Let me simplify this, and let's just say that it has to be a var declaration. It has to be given. This one has to be an expression there. So this will now just be DA or DCB. We gotta now update the print AST. We're going to remove this code. Whoops. And let's see if, let's go back to eval. And here we're going to remove A entirely. We're going to compile that. We're going to let Copilot kind of catch up. And then we're going back to our print AST to fix that up. And let's see if it can guess it correctly this time. Still no. That's all right. I don't really care too much about this, so I'm going to do D, C, B, and then we're just going to say print string for statement. That's it. And yeah, I guess we're not using them, so prefix them with underscores. Constructor for statement expects 4 arguments. I thought I already fixed that. No, I have not. Okay. The expression has type declaration, but an expression was expected to type statement. Aha, okay. Because this is actually not a statement. This is a declaration. Okay. Now, let's see what complaints we get. Eval statement scope D. This is an eval. Let's go over to eval now. So this should now be eval declaration. Okay, so now we got a parsing error. Let's take a look at our test logs file. Var a is equal to 0, var temp. For var b equals 1, a is less than 1 or 10,000, b is equal to temp plus b. Print a, temp is equal to a is equal to b. Okay. Fibonacci numbers also grow really large really fast, so I'm gonna make that go down to 10. But there's actually an actual parsing issue here. So let's take a look again at how the parsing's done. We have a for followed by a left parentheses, followed by a declaration, followed by, and actually technically that should be a var declaration. All right, let's take a look at our grammar here. Yeah, it needs to be a var declaration. I don't have a definition of a var declaration. Declaration has to map to an AST of declaration. Because I don't think I can put, yeah, I can't put var declaration in there. All right, followed by semicolon. Then we have the condition. Oh, we still need another thing here. So we are missing something. We have the var declaration. Then we have the expression for the condition. Then we have I for another expression. Actually, this needs to be a semicolon again in between them, followed by right parentheses, followed by a statement. So let's stick an I in there. Okay. AST now needs to be 2 expressions in there. Print AST just needs a small change to handle that extra I in there. Okay. And then eval now needs to have, okay, this is where we have the I now. Okay. So we eval the declaration. Then we say while eval expression condition, right? Then we eval expression scope I and ignore it. Does that look right? Yeah, that looks right. Okay, still parsing issues. Let's reopen the eval file to see if the LSP is better. Okay. So no complaints in terms of the compilation, but still not able to run this correctly. So maybe we actually want to finally take a look at our print AST thing, which ironically I didn't actually implement for this for expression. So, our for statement. Print statement, that one's actually going to be a print declaration init print string, print condition, print string, print statement, increment. That one's actually a print expression. Is that supposed to be an expression? Let me look at the grammar again. It is an expression. Okay. Print statement S. Yeah, sure. That looks fine. Unbound value print declaration. And. Okay. All right, so now let's go over to our main, and we're going to read file, we're going to parse, and then we're going to print. We're gonna print AST. Well, okay, I guess that makes sense. If it's failing at the parsing error, I don't even have an AST yet. Okay. So this is where not having implemented error handling is kind of biting me in the butt. Exception OCaml parser.men here basics.error. Okay, let's try wrapping this in a try here. Try And I know we implemented a try and eval somewhere. That was up here somewhere. With, and then whatever we end up getting. Try with, and what does that look like again? Try with, and then just the stuff there. Try with, okay, that's kind of cool. So this is now how we do this, a little bit of error catching here. I don't exactly know what this thing is that we are printing though. So let's just say A, and then try printing it. Has type exn, but an expression was expected of type string. So what is an exn? Is that an exception? A I don't know, it's kind of funny that doing that dot had some stuff on it. Exn, but expression was expected of type string. Okay, so let's figure out when OCaml exn is. Error handling. Exceptions. Try with foo unit. Predefined exceptions. Okay. I'd like to try and find, presumably there's like stuff inside that exception. To get a stack trace when an on-handle exception makes your program crash, you need to compile the program in debug mode. Or tag debug when calling OCaml build. Printing. To print an exception, use a module print exe. Comes in handy. For instance, the function notify user below calls the function if it fails, prints the exception on standard error. Okay, let's give that a try. This expression is type string, but an expression was expected of type unit because it is the left-hand side of a sequence. This expression has type string, but an expression was expected of type unit because it is in the left-hand side of a sequence. Do I need to open print.exe? I don't think I do, but yeah, I don't need to open it. Okay. Okay, so what it printed out was just, oh, we don't really want to raise it. Let's just do exit 1. There we go. So all it says is parser.menherebasics.error. So let's see what else we have in print.exe. We've got backtrace. Get backtrace in. There was an error message stack. Okay, let's see. Dot toString print backtrace slots print a. Print takes a function. Okay, let's figure out. Let's look up print.exe here. OCaml print.exe. Applies function to x and returns a result. If the evaluation of fnx raises any exception, the name of the exception is printed on a standard error output, and the exception is raised again. Okay, so we don't really want that. Print backtrace. Prints an exception backtrace on the output channel OC. The backtrace lists the program locations where the most recently raised exception was raised. Get backtrace, record backtrace, backtrace status. I just want like a better description of the error. All right, let's try the backtrace thing. Okay, it's not like in this. The function has type unit string. It is applied to too many arguments. It doesn't even need the exception to be passed to it. That's kind of strange. Okay, clearly not doing that right. And stack in printf, eprintf, there was an error, message, and stack. And then re-raise it. Okay, let's just copy this thing over here. No, I don't really want to do that. Okay, so we're trying to do this thing. We're catching the exception. Get backtrace just takes unit. Gives you the stack back. So see if we can do OCaml min here parse error and see if there's any declarative parse error reporting with min here. Monolithic and incremental. The monolithic approach is typical for Yak-like style tools. It produces a black box module with no user serviceable parts inside. There's one function of type lexing.lexbuff to token. Is that what we're using? Lexing.fromString. The incremental API is much more flexible. It makes no assumptions about the Lexer API. You just give it tokens, and it gives you the parser state that you can inspect and act upon. The downside is you are responsible for driving it. There's no just give me the AST function. Let's look at an example of driving the parser. The grammar and expression is a BNF-like with two notable additions. Rules are semicolon separated, and you can add a wait before tokens to influence how often an alternative is taken. For example, in this rule, the recursive alternative is 10 times more likely to be taken. The parser is at bnfparser.mly. There's no need to change anything in the parser to make use of the incremental API. Instead, we need to add one more module for its driver. Here is the code that you can use as a blueprint for your own driver after adjusting the module and type names. Match i.stack environment with lazy nil invalid syntax lazy cons i.element state. Try bnf parser messages.message with Okay. This might be a good one to revisit at some point, but with no state to connect on error is found on automaton stack, the parser stops raising the exceptioner. You can catch this exception in your code and print the lexbuff position to know where an error has been detected. And print the lexbuff position. Next comes one parsing function for each start symbol of the grammar. Here we have assumed that the one start symbol named main. So the generated file parser.mli contains the following declaration. Okay, let's take a look at how this is done again. We're taking the string, we're passing it to lexing.fromString, parser.program, lexer.readToken. Okay. If only tokens is specified command line, the type token is generated and the rest is omitted. Okay. The exception error carries no argument. It is raised by the parsing function main. Next comes one parsing function for each start of the grammar. Here we have assumed there's one start symbol named main, so the generated file parser.mli contains the following declaration. Okay, let's go back to when no state oops. The position of the error can be obtained by reading the lexical analyzer's environment record. In the incremental API, the parser rejects the input by returning the checkpoint rejected. Error recovery, error handling the new way. Okay, indeed, as soon as an invalid token is detected, the parser introduces a checkpoint of the form handling error. At this point, if one decides to let the parser proceed by just calling resume, then main enters its traditional error handling mode. Instead, however, one could decide to take control and perform error handling or error recovery in any way one pleases. One can, for instance, build and display a diagnostic message based on the automaton's current stack and or state, or one could modify the input stream by inserting and deleting tokens, so as to suppress the error and resume normal parsing. In principle, the possibilities are endless. Okay. So, how do we actually do that? All right, let's take a look at this code again. We know that we're having a parsing issue. Let's comment out some of this and then just try Okay, we have a var declaration, and then we have another var declaration of temp, and it's nil. Okay. So now let's just try doing print b. Okay, so already a parse issue. Oh, actually, I didn't complain about anything. That's curious. Is that because I'm suppressing it in the main now? Yeah, that's exactly what's happening. So if I go back to here, okay, yeah, back to our parsing error. Okay, so it's not parsing this correctly. For var b is equal to 1, a is less than 10, b is equal to temp plus b. Let's try something a little simpler. Let's just say var a, actually let's not even do that. Let's just say for var b is equal to 1, b is less than 10, b is equal to b plus 1. Okay, doesn't like that either. Let's take a look at our parser now. For left parentheses declaration. Now this really should be a var declaration, so maybe that's what's throwing it off right now. Followed by a semicolon. Okay, followed by an expression, followed by a semicolon, followed by another expression, followed by a right parentheses, followed by a statement. That's all looking fine. So let's maybe try pulling var declaration out as its own thing. I think that might mean having to pull it out in the AST as well. How do I actually want to do that? If I want to say this is just a var declaration. So this is not being parsed correctly. Surprised about that. I have all the tokens defined, right? Yep. For left parentheses, right parentheses, semicolon. They're all there. For left parentheses, declaration, semicolon, right parentheses, statement. Oh, you know what's interesting is that this var declaration itself is supposed to be terminated by a semicolon. Right. So let's try removing that. Because essentially it's looking for two semicolons there. Now we see an expression which does need to be terminated. The expression isn't terminated by a semicolon. So that needs its semicolon. And then we have another expression. Let's see if that likes it. Hey, look at that. Okay, interesting. Let's go back to the main now. And let's go back to eval here. Okay. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nice. We have a for loop working. Let's try going back to the code sample. Look at that. We got Fibonacci numbers. Nice. So there's a few things missing from here. Right now, we can't leave off any one of these things. We also can't replace this one with an expression. This one has to be a declaration. This one has to be, they all have to be there. And we're also not really doing it with the desugaring method. So I think I'm going to call it here for tonight, though. I'm glad we got something working. It took quite a while to figure that bit out. I have been pushing this error handling stuff further and further along, but I think it's starting to get to a point where I better have error handling to even help myself out with the development of this. But actually, let's maybe just finish off taking a look at these challenges here and read the design note on desugaring. A few chapters from now, when Lock supports first-class functions in dynamic dispatch, we technically won't need branching statements built into the language. Show how conditional execution can be implemented in terms of those. Name a language that uses this technique for its control flow. First-class functions in dynamic dispatch. Won't need branching statements built into the language. I'm not really sure about that one. There are plenty of languages out there that don't have conditional execution using branching statements. The one that comes to mind right now was just hit 1.0 last week, and that's Gleam. Gleam only has one way of doing conditional logic, and that is with something called a case, where it's kind of like a switch statement, but on steroids with pattern matching. So that's the only way. There's not even any if statements in Gleam. But I don't really know how that ties into dynamic dispatch. It might not in the case of Gleam. Likewise, looping can be implemented using those same tools, provided our interpreter supports an important optimization. What is that and why is it necessary? So that's probably referring to tail call optimization, because you can use recursion, but that ends up putting a whole lot of stuff in memory, and then your heap size grows and kind of explodes if you're not careful. Unlike locks, most other C-style languages also support break and continue statements inside loops. Add support for break statements. The syntax is a break keyword followed by a semicolon. It should be a syntax error to have a break statement appear outside of any enclosing loop. At runtime, a break statement causes execution to jump to the end of the nearest enclosing loop and proceeds from there. Note that the break may be nested inside other blocks and if statements that also need to be exited. That sounds a little complicated. Design note: spoonfuls of syntactic sugar. When you design your own language, you choose how much syntactic sugar to pour into the grammar. Do you make an unsweetened health food where each semantic operation maps to a single syntactic unit? Or some decadent dessert where every bit of behavior can be expressed 10 different ways? Successful languages inhabit all points along this continuum. On the extreme acrid end are those with ruthlessly minimal syntax like Lisp, Forth, and Smalltalk. Lispers famously claim that their language has no syntax, while Smalltalkers proudly show that you can fit the entire grammar on an index card. This tribe has the philosophy that the language doesn't need any syntactic sugar. Instead, the minimal syntax and semantics it provides are powerful enough to let library code be as expressive as it were part of the language itself. Near these are languages like C, Lua, and Go. They aim for simplicity and clarity over minimalism. Some, like Go, deliberately eschew both syntactic sugar and the kind of syntactic extensibility of the previous category. They want the syntax to get out of the way of the semantics, so they focus on keeping both the grammar and library simple. Code should be obvious more than beautiful. Somewhere in the middle you have languages like Java, C#, and Python. Eventually you reach Ruby, C++, Perl, and D, languages which have stuffed so much syntax into their grammar they are running out of punctuation characters on the keyboard. To some degree, location on the spectrum correlates with age. It's relatively easy to add bits of syntactic sugar in later releases. New syntax is a crowd pleaser, and it's less likely to break existing programs than mucking with the semantics. Once added, you can never take it away, so languages tend to sweeten with time. One of the main benefits of creating a new language from scratch is it gives you an opportunity to scrape off those accumulated layers of frosting and start over. Syntactic sugar has a bad rap among the PL intelligentsia. There's a real fetish for minimalism in that crowd. There is some justification for that. Poorly designed, unneeded syntax raises the cognitive load without adding enough expressiveness to carry its weight. Since there is always pressure to cram new features into the language, it takes discipline and a focus on simplicity to avoid bloat. Once you add some syntax, you're stuck with it, so it's smart to be parsimonious. At the same time, most successful languages do have fairly complex grammars, at least by the time they are widely used. Programmers spend a ton of time in their language of choice, and a few niceties here and there can really can improve the comfort and efficiency of their work. Striking the right balance, choosing the right level of sweetness for your language relies on your own sense of taste. It's really interesting that he's, I don't know, his opinion of syntactic sugar seems to be the opposite of what I've seen. I actually think that syntactic sugar can be a really powerful tool in the sense that you can define a language that is semantically very simple. And to make it more ergonomic for the user to use, provide these syntactical tools and sugaring to make it a little bit nicer. Good examples of this, I think, is Elixir. Elixir, I guess it's a little bit more than just, no, I would say it's still syntactic sugar. Almost all of Elixir is like a whole pile of macros built on top of Erlang. So much so that like when you dig down into like what makes up Erlang the language or Elixir the language, you find out that there's like some very minimal definition. In fact, you could write all of your Elixir code using only a single data structure, which are atoms and keyword lists. So you could get rid of all of your code and just let's actually maybe pull up an example. This would be an interesting thing to take a look at. A little bit off topic here, but in Elixir, you define a function by saying def some function, give it some parameters, you do that. Do this. So you do def ASDF A and B do A plus B. This def itself is just a macro. So you can then say something along the lines of, I think it's like def, you can call that ASDF, I think as a string, something to the extent of this is what it ends up looking like. This do ends up being a block in a keyword list. I don't know. It's not exactly that. But more or less, even the primitive constructs of the language, like even defining a function, is just syntactic sugar for something you could do without it. Now, I'm not saying you should do it that way, right? But as a programming language designer, it's really nice to have this really minimal semantic definition that you can map to higher level syntactic constructs. So anyway, that's a quick little deviation. I will be attempting to clean this up. I'll poke around a little bit and then we'll maybe do a follow-up video on how to implement this for loop correctly, first of all, and then secondly, how to perhaps do it using desugaring instead of doing it in the actual interpreter. But I'll see you in the next one.